Steven Weinberg was a Nobel laureate, statesman of science, and voice of reason. He was universally regarded as one of the greatest thinkers of our age. I first met Steven Weinberg back in about 1986 when I was a graduate student at Harvard and was invited to give a talk at the University of Texas, Austin, where Professor Weinberg was the head of the theoretical physics group. Now, I almost never get nervous before talks, but this time, knowing that Steven Weinberg would be in the audience, I was seriously nervous. I mean, so much of my outlook on physics had been shaped by Professor Weinberg's writings. I mean, when I was in high school, I'd read and reread his book, The First 3 Minutes. And in college, his textbook, Gravitation and Cosmology, Principles and Applications of the General Theory of Relativity, well, that textbook had been a kind of companion to me. I purchased it after a lecture by Stephen Hawking got me all fired up about space and time, cosmology, relativity, and all that. And I desperately wanted to understand all the math and all the ideas, but back then, I was still a couple years away from having the necessary background, so I simply carried the textbook around with me. Everywhere. Steven Weinberg was always in my backpack. And when no one was around, I'd sometimes take out the text, admire its rich blue cover, sometimes running my fingers over the title, and when later on, I finally was able to dive in and understand the material, I felt like I'd journeyed through the cosmos with the rigorous but crystal clear Steven Weinberg as my personal guide. So you can understand how going to Texas to give a talk and meet Weinberg in person was for me quite the moment. Well, the talk went off without a hitch, but it was my conversation with Steven Weinberg just after the talk which really stuck with me. In my graduate student eagerness, I had thoroughly stuffed the talk with complex equations, but with great tact after the talk, Professor Weinberg gave me his own down-to-earth version of many of the points that I had made myself in the talk. It was a virtuosic demonstration of Weinberg's hallmark capacity to see through complexity and reveal the essence of ideas, a capacity for which Steven Weinberg was the unmatched master. With Steven Weinberg's passing, we have lost not only a giant of science, but an extraordinarily erudite, thoughtful, and sharp-witted observer of the human condition. He was a great friend to the World Science Festival, appearing many times in our programs, which allows us now to hear from him in his own words, reflecting on science, life, the state of the world, and where things are going from here. Professor Weinberg's own journey began simply. Like many theoretical physicists, from an early age he could feel the strange and wondrous power of mathematics to illuminate reality.
I grew up in a modest family. I was the first to go to college. I found, to my amazement, teaching myself some physics and mathematics in high school, that you could do powerful things with this intellectual apparatus. I remember calculating the shape of the cables that hold up a suspension bridge. It's a catenary, and deriving the equation for a catenary. I thought, wow, I'm not building a bridge, but I can see why it takes the shape it does. And that sense of the power of mathematical reasoning was intoxicating. And of course, calculating the shape of a suspension bridge cables was nothing new, and there was nothing I could publish about it. But I love the the intellectual power, and then eventually found I could do something myself. It took me a long time, actually. I wasn't at all precocious. In college, the idea of doing anything new seemed infinitely difficult because there was all that work out there that had already been done, and I hadn't learned it all. And I thought you had to learn everything in order to do anything new. And then when my wife and I got married, we decided for purely romantic reasons to spend our first year in Europe. And I went to the Niels Bohr Institute at Copenhagen with a bag of books that I was going to read, again, thinking I wasn't going to do anything original. And they said, well, no, everybody here is doing research. You've got to start doing research. I said, you're kidding. I don't know how to do anything new. And one of the professors there, who died recently, Gunnar Chalane, actually suggested a research problem. And I didn't know much about the subject, but by God, I could do the problem, and did it and got a paper published. And so by the time I arrived back in graduate school at Princeton, I felt like a grown-up. And I'd made that transition from being a student to being a grown-up. And it was really a difficult transition, which, you know, it's like getting rid of your skin, like a snake getting rid of their skin. But it's gone pretty well since then.
After making that difficult transition from student to researcher, some scientists are content to drill ever more deeply in the circumscribed area in which they've gained expertise. Steven Weinberg took a completely different tack, drilling deep for sure, but also constantly surveying the intellectual landscape, observing and appreciating dependencies and connections that had escaped earlier generations of thinkers. And among these was the recognition that the arrows of explanation point toward the most fundamental and far-reaching principles of physics, being of profound relevance not just to physics per se, but to our understanding of nature at all levels of explanation.
The world is governed by a unified set of laws, which we don't yet know, but that physics and chemistry are not separate sciences. And even biology, as strongly influenced as it is by historical accidents, like the shapes of the continents and the fact that a comet may have hit the Earth 65 million years ago, biology itself doesn't have independent laws. There's no biological law that says organisms have to evolve to get better. That's a consequence of natural selection acting on inheritable variations, which was really only, although it was stated by Darwin, it was doubted, and it really only became well established with the neo-Darwinian synthesis in the 20th century. So I think that's a big thing. You know, at the turn of the 20th century, people were writing articles about whether physics is finished. And I couldn't understand how anyone could think that because, of course, physicists had not succeeded yet in even beginning to explain chemical laws, why sodium and chlorine form a stable compound, for instance. And so how could they think physics was finished? And the answer was they didn't think that chemistry was the job of physics. That was something for the guy down the hall. And the unity of science is something we've learned. I guess you could say we've unlearned the idea that there are separate, independent principles of physics, of chemistry, of biology, all standing at the same level of being equally fundamental.
With that unlearning of the natural but naive supposition that all of the sciences have an equal claim of being fundamental, finding the laws that undergird the most fundamental of sciences, physics, that becomes all the more pressing. Einstein himself dreamed of encapsulating the laws of physics in a single coherent mathematical formulation, the so-called unified field theory. In its more modern formulation, a unified field theory would establish that all of nature's forces are merely different manifestations of a single, all-encompassing superforce. Famously, after ardently pursuing this goal for over 30 years, Einstein came up empty-handed. Taking a different approach, Steven Weinberg was able to bring this dream of a unified theory one step closer. He proposed that two of nature's forces, the electromagnetic force, which is responsible for all electric and magnetic phenomenon, and the weak nuclear force, responsible for radioactive decay, he proposed that they are actually different facets of a single force, which is now called the electroweak force. In the 1970s, a series of experiments confirmed Weinberg's proposal, leading to his sharing the 1979 Nobel Prize in Physics. Around that time, John Preskill, who is now the Richard Feynman Professor of Theoretical Physics at Caltech, he was working on his dissertation under Steven Weinberg, and John joins us now from his home in California. Welcome, John.
Glad to be here, Brian.
Thank you. You know, it's so nice of you to join us for this celebration of the life and work of Steven Weinberg. You were one of his PhD students, and I was actually your student back in, I think it was 1981, in classical mechanics class. So in some poetic sense, there's a physics lineage between us all, which is a nice thing. So thanks again for joining us. How did you first meet Steven Weinberg?
Well, it was when I was a prospective student. I had just applied to Harvard. I didn't know yet whether I was going to get in. And my then fiance, now my wife, Roberta, and I were in Boston for the day just for fun. And we thought on kind of a whim, well, let's go to Harvard and look around there. Let's find out what the physics department looks like. And it just happened that Steve Weinberg was in his office. And, I'm usually a pretty shy guy. And so it seems a little amazing to me now because, I've met with many prospective students over the years at Caltech, and I can't remember any one of them ever coming to see me with his fiance, but that's what I did. I came in, I said, Steve, this is, I also said, Professor Weinberg, this is my fiance, Roberta, and I'm interested in getting a PhD at Harvard, and I'd just like to hear a little bit about your research. And he didn't act like there was anything unusual about that. In fact, he said, oh, Louise and I did the same thing. He and his later wife and fiance had also looked around at graduate schools together. So it seemed very natural to him, and we had a very friendly chat.
And obviously you were convinced that this is the place that you wanted to go. And is it, I heard that Professor Weinberg actually met with your parents at some point.
Well, that was later, around the time that you were taking my class, I think, probably around 1981. I was a faculty member at Caltech then, an assistant professor, and my parents were visiting us, and I knew they'd really enjoy meeting Steve. So we had him over for dinner. It was the summertime. We had a pool in our backyard. We all went for a swim. I grilled chicken. We ate dinner outside. And Steve, I think, realized that I was kind of trying to impress my parents, that I was a colleague of the great man. And he played that role superbly and treated me with, considerable deference beyond what I deserved. But the most memorable thing about that evening for me is at one point, for some reason, we were talking about how you make ice cream. And Steve said, I always wondered, why are you supposed to put salt in the ice cream maker? And my dad said, well, isn't it so it'll lower the melting point of the ice so the ice cream will get colder and solidify? And Steve said, of course, that's it. Thank you. And he may have played that up a little too, but for my dad, it was fantastic because he could gloat for the rest of his life for the next 20 years about how he had taught science to Steven Weinberg.
And was that how Steven Weinberg was? I mean, was he generous in terms of spreading around, credit for ideas and making people feel good about the process of research and discovery?
Well, I wouldn't say that was, the first character trait you would associate with him. As a scientist, he was very solitary, unusually so. He was not so much of a collaborator. In fact, this morning I was kind of browsing through some of his best known papers. And I looked at like the top 50 or so in citations. 42 of those are single author papers. He just
Yeah.
didn't collaborate very much. It wasn't natural for him. He liked to think things through for himself. And of course, he did give credit. He was very meticulous about citing people. And also, he was a little bit sensitive if he didn't get cited when he thought he deserved it. And so, he appreciated that other people would expect the same treatment. And so he was very careful about that to give credit when it was deserved.
Now, one of those solitary papers was the 1967 paper in which you put forward ultimately the work that he would receive the Nobel Prize for. But by the time you were his student, that work was kind of old. I mean, it wasn't passé, but it had been around for a while. Was he still thinking about Electroweak Ideas in the mid-70s, or did he do that work and just sort of let it go and just would see what would happen?
Well, he was sort of on to the next thing. He was interested in grand unification, for example, the next step in unification. And he was interested, in those days, we were hoping people would detect proton decay. Maybe they still will, which would give us some insight into particle physics at very short distances. He was interested in that. He was interested in what we now, and I guess even back then, call beyond the standard model physics. What else is there that we might discover in the next generation of accelerators? Of course, in those days, we were thinking ahead to the SSC, which sadly was never built. But that all those things influenced me. It was Steve's style with respect to how he interacted with students was similar to his style when it came to interactions with other scientists, not so much of a collaborator. And he inspired me in many ways when I was a student, but a lot of it was from reading his papers and trying to absorb and digest his ideas rather than in one-on-one contact. When we did talk, he was often pumping me for information. Steve always was trying to learn something new. And if there was some topic that I had studied in more detail than he had, our conversations would be focused on him trying to find out from me what I knew that could help him. He was
Right.
always like that in interacting with other scientists. He wanted to find out what somebody knew that was relevant and helpful for his own work.
Yeah, we once had a long conversation about deformations of complex structures of Calabi-Yau manifolds. And, he, by the end of that conversation with me, I think knew more about the subject than I did. And I'd sort of been working on it for years. But after the 1967 paper, it wasn't like he put out this paper and the world of physics just said, yes, this is the answer. I mean, it took a number of years before people really took notice of these ideas. And as experiments in the 70s began to make it clear that Electroweak unification was right, no doubt there was a sense that this was Nobel-worthy work. So was there a kind of sense around Harvard in the October fall period of each year, a kind of tension waiting to see if this might be the year when the Nobel Prize went to Steven Weinberg?
By the late 70s, that was the case, yeah. It was just as you described, for about 4 years after that 1967 paper, the ideas really didn't catch on very much. You can see that in the citation record.
Sure.
Not many people were following up on it. It changed rather abruptly in 1971, in particular because of work by 't Hooft and Veltman and others that sort of made it clear that the theory really did make sense mathematically. And then interest in it really started to skyrocket. And then by 1973, experimental evidence was starting to pour in, supporting the predictions of the model. But there was still controversy for a while in the mid-70s. Is that really the right model? How well do we know that? How convincing are the experiments? Pretty well settled, though, by 1978, in particular by experiments in SLAC, in which they saw that left-handed and right-handed electrons interact with nuclei differently, as the theory predicted. So by the late 70s, every October, there was kind of some anticipation. Maybe this is the year, because it seemed like this was clearly a Nobel-worthy discovery. And adding to the drama was that Steve and Shelley Glashow, who were both Harvard faculty members with offices on the same corridor, were both Nobel Prize candidates. So of course, the nightmare scenario was that one of them would get the Nobel Prize and not the other, but luckily that did not happen. And in 1979, when they shared the prize with Abdus Salam, that was an exciting moment.
And so what were you there? I mean, when Steve found out? I mean, I mean, it's just like champagne and excitement. I mean, how did Steve respond to this accolade?
He was nonchalant, you know. I'm deep, no, with his sense of the history of physics, I think he very much appreciated the significance of receiving this honor. Who wouldn't? But he kind of brushed it off. You know, he was teaching a class and he had prepared the class the night before. You know how it is. You get the call in the middle of the night if, you know, you're in the US or very early morning, and then you're not going to go back to sleep, and it's all very exciting. But he had been up the night before preparing his class, so he was going to teach that class come what may, and he did. He went ahead with the class. He said, I prepared this class. I'm certainly, you know, not going to waste all that preparation time and not teach it. And he did. But of course, he was very, very proud to receive that recognition.
Just to get a sense, I mean, where would you place Electroweak Unification in sort of the pantheon of great physics breakthroughs? Is it up there with, you know, Einstein's insights? I mean, where would you place it?
Well, that's a pretty high standard, isn't it?
Yeah.
But I would certainly say in the historical sweep of physics, it was a major milestone. You know, in physics, there has been a steady march towards a more unified and complete understanding and description of how nature works. And so, you know, there were events like recognizing that the terrestrial and the celestial could be combined in a universal theory of gravitation. That was Newton. And Maxwell realized that electricity and magnetism fit together in a way, you know, they couldn't really be separated. And Einstein realized how to get special relativity to fit together with the theory of gravitation, a great step forward as well. And this was a significant step in that progress, because now we had a unified way of describing two of the forces, electromagnetism and the weak nuclear force. That's what Steve's model was all about, and also the contributions of Glashow and Salam and others. And, you know, if you look back over what's happened since in fundamental particle physics, there has not been any comparable advance, I think, since then.
And so would you say that there was a particular approach to physics or a style of thinking about these problems that is responsible for propelling Weinberg to have made this advance where nobody else had really for a long time before or a long time since?
Well, I'll tell you, I find that a hard question to answer, and here's why. Steve was not a model builder. That wasn't his style. His style was to be very methodical and general, and he was masterful at that. He would try to, you know, figure out what the ground truths were on which you could build deeper knowledge. And many of his papers are like that, very general arguments starting from first principles. He didn't like building models himself. He appreciated it when other people did it, because he figured, well, a model is just a model and it's not going to really be right. You know, it's not going to be the right answer to how nature really behaves. It might teach you something. He would rather give a more general argument that would apply to models that people might dream up in the future. This paper wasn't like that. It was a model. And I think another thing that was a little uncharacteristic was Steve was not so much the type of scientist to have an aha moment, you know, a flash of insight, and suddenly I see the answer. He was more, like I said, he had a methodical style. And but this was a flash of insight. He was working on a somewhat different problem, trying to understand properties of the strong interactions, and he suddenly realized that wasn't working, but the same concepts could be applied to a different problem, which was this unification of electromagnetism and the weak nuclear force. So it was very uncharacteristic of his career, really, that he had that flash of insight. Of course, it, as was more typical of him, you know, that built on some years of thinking and experience with the types of, we call them gauge theories, that eventually turned out to provide the answer.
You know, around that time, he must have been working in parallel on his first popularization of physics, like the first 3 minutes. Were you aware that he was writing a popular book? I mean, was he writing that book when you were his student?
He was, and in fact, the story of the book is that he gave a public lecture. This was a little before your time at Harvard, I guess, but it was, it was in the Science Center, completely full audience, and he talked about the early history of the universe in that public lecture. And he made a joke in that talk. He said, and then after the first 3 minutes, when the helium had formed in the universe, not much happened after that. It was, the story was kind of over after the first 3 minutes. And it turned out that a publisher, heard from a friend about that joke and thought, boy, this could make a very interesting book. So Steve wound up getting contacted and asked whether he was interested in writing a book. And he decided he was. He had written a textbook on gravitation and cosmology. And that's a little unusual because that wasn't his area of science.
Yeah.
Right? He was a particle physicist. And there's something pretty interesting about that book, which we haven't really talked about this yet, but about Steve's style. He was a very non-visual thinker, and in particularly, well, Brian, in general relativity, it's a rather visual subject. It's about geometry. People draw diagrams. If you're Stephen Hawking or Roger Penrose, you think visually about those things. Steve did not think that way. And it's quite striking to look at his book on gravitation. There are no pictures.
Yeah.
He didn't like pictures. In fact, here's another funny thing is when he got his first PC, for some of your viewers may not know, but there was no Windows then. It used to run on another operating system called DOS, MS-DOS. You just type into the command line. And when Windows came out, Steve didn't like Windows. He didn't like icons. He wanted to just type on the command line. He just didn't think in terms of visual things.
Yeah.
He thought that people put too many gratuitous pictures in their papers. Why do you need the picture? It's all in the equations.
Well, I think, and maybe in some editions of his textbook, there's a footnote, a famous footnote, where he says any similarity to the differential geometry that had been developed that Einstein made use of, which is a very visual subject, that was just sort of a coincidence. It wasn't the heart of the general theory of relativity. And I don't know if he ever changed his mind on that perspective.
I'm not sure, but of course, you and I know that's not the whole truth.
Right.
And in fact, around the same time, another great book on relativity came out by Misner, Thorne, and Wheeler, and it was full of pictures because John Wheeler was a very visual thinker.
And
anyway, about that book, yeah. I mean, it would turn out to be a very influential book, the first 3 minutes. And it was intended for a lay audience, but it's a pretty technical book. I think it's pretty hard going for people who don't have scientific training. But it was read by, and I think had an influence on a lot of scientists.
Yeah, certainly on me, for sure. Was there any pushback in that era of someone taking time out of research to write a general book for the general public?
I don't think there was really pushback. I do remember one incident where this doesn't really qualify as pushback, but you kind of brought it to mind. Leon Letterman came to Harvard and gave a talk, the physics colloquium, and he started out with a joke. He said that he had heard that Steve had written a book, and so he went to a bookstore to look for it. And he said, "Do you have the book, The First 3 Minutes?" And whoever was helping him in the bookstore said, "Yes, we do, and we're selling a lot of them." And Letterman said, "Well, isn't that kind of strange that a book about science would be selling so well?" And the reply was, "Science? I assumed it was a sex book." And so Letterman thought that was a pretty good joke.
Yeah, I think Letterman made that up, is my guess.
Yeah.
Known Letterman, yeah.
Right.
So when one thinks about the remarkable life of Steven Weinberg, and as students are going to continue to read his many textbooks, Gravitation and Cosmology was just one of them, as students continue to learn about the Electroweak Unification and all the other contributions that Steven Weinberg had such a vital role in, is there something that students you feel should take away from his approach to physics that can help guide their own trajectory, guide their own course through research?
Well, I'm sure there are many things. Of course, we're all different and different scientists succeed in different ways. So what worked for Steven Weinberg might not be the best method for somebody else, but he was very successful at identifying the right problems. This is the key in many cases to making scientific progress. And the right problem should be one where you have a good chance of making progress, even if you can't solve it completely. But where it'll really have some impact and advance our understanding in a significant way if you do make that progress. And Steve did that again and again. So I think it is important for students to be very thoughtful about the things that they work on and to keep those criteria in mind, that you want it to be something you can really do. And of course, different people have different strengths and weaknesses. So that's kind of a personal decision about where you think you can push progress forward. But also, if you succeed, how will it give us a deeper understanding of science at some fundamental level? That was one of his strengths. And we haven't really emphasized, except for the first 3 minutes, how, particularly in his later career, he was a marvelously effective scientific communicator. The essays he would write for the New York Review of Books, many of which were collected in books that he published, can be guaranteed to provide interesting insights. Any subject that caught his interest, he could write about with exceptional clarity and with a real intellectual honesty. He would tell you exactly what he thought and he would explain why. And he did that with great respect for the reader. I think this was an important thing to realize about Steve as a communicator. He appreciated that there are people who are not scientifically trained, but are just as smart as Brian Greene or John Preskill, or people who do have some training in theoretical physics. He didn't talk down to them, but of course he realized that you couldn't talk to them in jargon. And so he had a very strong gift for communicating things through clear language and good examples and analogies.
Yeah, he was certainly a spectacular writer, thinker, so much insight in his essays and articles, and of course, one of the great scientists of our age. So thank you, John, so much for your insights into Steven Weinberg. We appreciate it greatly.
All right, it was a lot of fun, Brian.
With all the advances in understanding the basic laws and properties of nature, that understanding nevertheless had significant limitations. And no one was more aware of that than Steven Weinberg.
We have a very good theory of all the particles and forces that we can study in the laboratory, which I gave the name, the Standard Model, which seemed to me not excessively immodest. I mean, biologists have something called the central dogma, but it works, and in an almost boringly repetitive way, we keep testing it. The discovery of the Higgs boson a few years ago turned out to just fit what was expected. The Standard Model predicts all of its properties except its mass, and it was found with all those properties. And now we know the mass experimentally. It would be tragic if the only thing we did at the Large Hadron Collider or anywhere else was to go on elaborating the verification of the Standard Model. And because the Standard Model is certainly not the end of the story. I mean, no one thinks it is. It has a lot of unexplained features like numerical quantities, ratios of masses. We don't know where they come from. It doesn't include gravitation, which is a big thing not to include. And we're we're happy with it as far as it goes. We desperately want to go beyond it, and we may not be able to in our lifetimes.
In that remark, Weinberg captures really well the kind of mixed feelings that many physicists have regarding the Standard Model. It is undeniably, utterly remarkable that with a mere handful of mathematical equations, the equations of the Standard Model, physicists can explain every piece of data collected at every particle accelerator in the world, as well as data from cosmic rays and a great many other astronomical observations. All the same, the Standard Model is based on a number of key assumptions that so far scientists have been unable to explain from some kind of deeper understanding.
In the Standard Model, there is a somewhat mysterious list of particles that appear in this theory as elementary particles. Among them are quarks. Two kinds of quarks. The lightest ones make up the protons and neutrons, which in turn make up atomic nuclei. 3 quarks in each proton or each neutron. But there are altogether 6 types of quarks. The other 4 are heavy and unstable. They're all equally important as far as the Standard Model is concerned. It's just an accident that 2 of them are the ones that appear in ordinary matter. There are other particles. There's the electron, and it has a couple of siblings, which are just like the electron, but heavier and also unstable. Now, we have a table based on experimental data of the properties of these particles, their masses especially. And we know what their masses are, but we don't know why they are. We've been looking at this table of experimental information about these masses now for several decades with the feeling that it's got to be telling us something, and we don't know what it's telling us. It's a little bit like having a manuscript in a, say, linear A, a language that hasn't been deciphered. You feel you ought to know what it's saying, but you don't know what it's saying.
What's more, even with Weinberg's synthesis of electromagnetism and the weak nuclear force, and even with the Standard Model's capacity to explain the behavior of familiar matter, if not its intrinsic properties, observations and data establish that the Standard Model is demonstrably incomplete as a description of nature, a realization that has driven much of physics over the course of the past few decades.
Another thing, astronomers tell us that 5/6 of the matter of the universe is some kind of dark matter, which was discussed already in a panel in this festival. This dark matter, none of the particles of the Standard Model have the right properties to make up the dark matter. So 5/6 of the mass of the universe is not in the form of anything described by the Standard Model. Well, it's something we ought to know more about. And finally, there's a little technical detail that gravity doesn't fit in the Standard Model. It's also something we would like to know more about. So we have to hope for more insight from the next generation of experiments at big accelerators, like the one that I mentioned before at the Large Hadron Collider in Europe. Now, that is pretty big. It's 17 miles in circumference. It's not visible from space because it's buried in a tunnel which goes across the border between France and Switzerland. In this accelerator, 2 beams of protons are going round and round, kept in their orbits by powerful magnets. The magnets have a strength, roughly 10,000 times the strength of the Earth's magnetic field, which acts on compass needles. When the Large Hadron Collider gets up to its final design capability, it will accelerate particles to an energy which is about 7,000 times the energy contained in the mass of a hydrogen atom. It's an energy which is about 1,000,000 times the energy of the alpha particles in Rutherford's famous experiment. It is certainly big science. It's also big science in another sense, a human sense, which is not so good. One experimental team at the Large Hadron Collider that I happened to look up for this talk, the ATLAS collaboration, has over 1,000 PhD physicists working together. They'll all sign the research articles when they come out. The title page will be much larger than the rest of the article. And I don't know how a young experimental physicist can make a name for himself or herself working in a collaboration like this. Also, the experiments from planning to completion take over a decade, which is a fair fraction of a scientist's working career. And it may be an experiment which turns out to yield nothing exciting. So I just thank heavens every day that I'm a theorist. I don't have to do that. But we're forced into the mold of big science by the logic of the subject. At any one moment, the particles that we know about are those that have a low enough mass so that they can be created at existing accelerators. And if you want to find new forms of matter to fill out our picture of the way the world is governed, then you have to have higher energy. And we can't help it. The purpose is not to get records for the number of particles or the energy. It's to learn about the laws of nature.
Weinberg's point is that physicists seek out new particles not to add to some kind of taxonomy of ingredients, but rather to glimpse the foundational laws and principles of which the list of particles is a prime manifestation. That is, the knowledge of particles and the understanding of their properties and interactions is the sharpest means that we have for deducing the fundamental laws.
There's one particle in particular that we expect without certainty to be produced at the Large Hadron Collider. It's a particle called the Higgs Boson. It is predicted as a necessary feature of nature by a theory that unifies the weak and electromagnetic forces that Brian mentioned in his kind introduction. In this theory, I should explain, the weak nuclear forces are forces that act inside the atomic nucleus, allowing neutrons to turn into protons or protons to turn into neutrons. They're very short range, and hence they only act inside the nucleus. The electromagnetic forces you all know about, that light that's staring me in the eyes, is an electromagnetic wave, and we've all felt the force of magnets pulling on a piece of iron. They seem very different, but in the equations of the theory, they are treated the same way. Also, in the equations of the Standard Model, the particles that I mentioned earlier, the quarks and the electrons and so on, have zero mass. Yet obviously that's not the way nature is. What you have is a situation where you have equations with certain very great simplicity, a great degree of symmetry, a symmetry between the weak and electromagnetic forces, for instance, a simplicity that says all the masses are zero, and yet that's not realized in the solutions of the equations, which describe what actually we see in nature. How does the solutions not respect the symmetry of the equations? Well, there are various ideas. The simplest idea, which appeared in the original version of this theory, invokes a new set of fields in addition to the electromagnetic field and all the other fields of the Standard Model, a new set of fields which pervade the universe, one of which would be manifested as an actual physical particle, electrically neutral, heavy, unstable, which has come to be called the Higgs boson. And this particle, if it exists, will be found at the Large Hadron Collider, because we know enough about it to know that its properties make it findable.
Well, the Large Hadron Collider did indeed settle this question by finding the Higgs boson, the elusive particle whose corresponding field pervades the universe and, like a cosmic bath of molasses, exerts a drag force on other particles that appears to us as the particle's mass. The confirmation of the Higgs particle concluded the experimental verification of the standard model of particle physics, for which Steven Weinberg was a prime architect. Nevertheless, the deficiencies of the standard model to this day still remain. No one knows why particles like electrons or quarks have this or that mass or electric charge. No one knows how to incorporate dark matter into some kind of extension or revision of the standard model. No one knows how to incorporate gravity into our fundamental description of nature's elementary particles. But these questions of the small and the ultra small are not the only ones that fascinated Steven Weinberg. Gravity and the cosmos inspired an equally passionate urge to understand.
You know, we talk endlessly about black holes, but we don't see black holes. All we see are the accretion disks around black holes, and we've become convinced that there are black holes in there, but we can't do experiments or direct observations on black holes. The whole thing is just terribly frustrating, and for the time being, I'm much more excited by the experiments that we were hearing about from LIGO, and hoping advanced LIGO goes on the air soon and discovers coalescing neutron stars, something we get our teeth into.
Indeed, just as Steven Weinberg anticipated, LIGO, the Laser Interferometer Gravitational Wave Observatory, has now seen coalescing neutron stars as well as colliding black holes, leading the way to a new era of observational astronomy that promises unparalleled insight into the cosmos. But as Weinberg also noted, even with such insight, it seems likely that some of the deepest questions will be with us for generations to come.
Well, the question I'd like to answer, I don't think will be answered in our lifetime, even your lifetimes, let alone mine, is what are the laws of nature? But more specifically, are we getting a good sample of the laws of nature as really fundamental, or is the Big Bang that we see just one tiny part of a much larger universe in which what we call the laws of nature vary from one part to another? I'd like to know the answer to that, and I hope the answer is that this idea that the universe is much bigger than just what we see, called the multiverse idea, is wrong, because then although there are suggestions that it might be right, but it would mean that we can calculate much less, just as Kepler was wrong in thinking that we can calculate the distances of the planets from the sun from first principles. We may discover that a lot of the things that we think we can calculate from first principles are just environmental parameters. That would be very sad, but it may be true.
Weinberg was not only a towering theoretical physicist, he was also a great expositor and writer. Not many physicists regularly published articles in the journal Nuclear Physics B and the Physical Review, as well as in the New York Review of Books. For Weinberg, the writing of science, both research papers and popularizations, was a solitary undertaking, but the process of science, the exchange of ideas, that was a source of incomparable joy.
I don't collaborate well, mostly because I like writing, and whoever else collaborates with me, I always like to write the paper. So why not just write it? But I love the sense of collaboration, that we talk a common language, and when I talk to other physicists about what they're doing, about what I'm doing, we understand each other. And I love that, being part of a circle of fellow workers. I remember when I was in high school, I saw the movie The Red Shoes. And of course, it's a gorgeous movie and bowled over by the music and the dancing. But one of the things that got me about The Red Shoes was the sense that there was the set designer and the composer and the choreographer, and they were all working together, and they all knew what each other were doing, and they spoke a common language. And I thought that that was wonderful. And you feel a little bit like that in physics, especially when a theorist talks to an experimentalist, because we have very different skills, but we're all interested in the same questions.
Weinberg complemented his groundbreaking capacities in fundamental science with a deep immersion in history. He was always careful to say that he was not an historian, but his insights about the future were thoroughly influenced by his understanding of the past. And as he looked to the future, he gave us words of caution and wisdom.
I gave a talk at the World Science Festival, the only other time I've been here, a few years ago, called The Crisis of Big Science, fearing that science had reached a point where we really have to build these enormous accelerators and observatories in space. We've answered the questions that can be answered with string and sealing wax, in Lord Rutherford's famous phrase. And society may be giving up on us. We saw the cancellation of a great project to build a large elementary particle accelerator in the United States. Incidentally, it was in Texas, but I was for it before that site was chosen. And we felt, well, you know, America, which had been at the forefront of this kind of really fundamental scientific research, was now surrendering that position. Fortunately, physicists in Europe picked up the torch, and we've seen great discoveries made at the Large Hadron Collider in Geneva. But it's possible that it's coming to an end, and that just as in the scientific revolution, scientists look back over the Middle Age, back to Hellenistic Greece, some 2,000 years earlier, perhaps our descendants will look back to the 20th century as a golden age, which began to peter out in the 21st. Well, as you can imagine, I hope that's not true. And I don't know that it is true, but I fear it may be.
Steven Weinberg developed some of the most far-reaching insights into the nature of reality using some of the most abstract techniques which experiment has shown essential to our mathematical articulation of physical law. In this way, Weinberg paralleled the journey taken a century ago by Albert Einstein. Einstein often described his quest as seeking to understand the mind of the old one, a quest for the workings of nature that Einstein referred to with what he described as a religious reverence. Steven Weinberg shared that reverence for the power and beauty of mathematical explanation, but he also made clear that none of these insights suggested to him a higher power or an overarching purpose to human life, a realization that for Weinberg was a source of freedom and nobility.
Well, I think everything's pointless in the sense that there's no point out there to be discovered by the methods of science. It's not to say that we don't create points for our lives. For many people, it's their loved ones, living a life, helping people you love. That's all the point that's needed for many people, and it's probably the main point for me. And for some of us, there's a point in scientific discovery and other points, but these are all invented by humans, and there's nothing out there that supports them. And it's better that we not look for it. In a way, we're freer. In a way, it's more noble and more admirable to give point to our lives ourselves rather than to accept it from some external source.
I could not agree more. Everything we've learned from science points toward life and we human beings more particularly as being nothing but sophisticated biological machinery composed of the very particles and influenced by the very forces described by the mathematics of the Standard Model. And much as an electron or a quark has no point to its existence, has no intrinsic meaning or purpose in its existence, large collections of such particles, like you and me, we have no intrinsic meaning or purpose either. Now, that can sound bleak. I even recall hearing Steven Weinberg on occasion describing this outlook as bleak. But I'd suggest an alternative perspective that I hold to be utterly essential, a perspective that resonates well with Weinberg's remark that it is more noble for us to find meaning and purpose on our own, rather than accepting it from an external source or power. How stunning and how spectacular it is that we biological machines, governed by physical law, have the capacity to rise above moment-to-moment survival and invent concepts, including purpose and meaning, as well as beauty and wonder and insight and understanding. And how fortunate we all are that one such collection of particles, Steven Weinberg, in his brief moment on the cosmological timeline, so profoundly deepened our grasp of those concepts, allowing us all to stand on his shoulders and see that much farther.